Okay, in the last class, somebody asked me the question about the point at which we ended. We said that there are two ways of approaching the problem when you have complex conjugate eigenvalues. One was if you just say that the two eigenvalues will be complex conjugate, therefore, the two eigenvectors will also be complex conjugate, and as a result of which the two eigenvalues and eigenvectors do not contain independent information, they have the same information. So, you will use one of them. The other is to say that no, we will go the same way as we did earlier. We will have the two eigenvalues, two eigenvectors, and we will write the equation x t as C 1 v e to the power that will be sigma plus j omega t plus C 2. This will be the conjugate of v. So, I will write it like this, e to the power sigma minus j omega t, right. Now, then we said that this right hand side in general will be complex, but the left hand side must be real, which is true only if the C 1 and C 2 are also complex conjugate of each other. So, C 2 actually is C 1 bar. Now, when that is so, then the two real parts are the same, the imaginary parts are one in the positive direction, one in the negative direction. So, if you want to extract the real value, then it is x t, the imaginary parts will cancel each other. So, you have twice of the real part, that is why we said twice of the real part of C, which is both C 1 and C 2, v e to the power sigma plus j omega t. So, that was the logic, but here if you actually do it, you will ultimately get the same result as you did with the other approach. So, let us illustrate this other approach with one example. So, let us take an example to clarify the point. Consider a system x dot is equal to sigma x minus omega y and y dot is equal to omega x plus sigma y. This omega and sigma could be any number, but we have just chosen one. The reason will immediately be clear, because what will be the next step? You will say that the matrix equation is x dot y dot is equal to sigma minus omega sigma x y, right, and then we will proceed to obtain the eigenvalues of this. Just do that. It will be obtained from the determinant of sigma minus lambda minus omega sigma minus lambda equal to 0, which will give, you see, yes, sigma minus lambda square plus omega square is equal to 0. So, if you expand it, you have lambda square minus twice sigma lambda plus sigma square plus omega square is equal to 0. Now, you obtain the solution, lambda is equal to twice sigma plus minus root over 4 sigma square minus sigma square minus 4 omega square, right, by 2. This cancels off, you are left we are left with sigma plus minus j omega. That is why we chose that equation actually, because this is a nice complex conjugate eigenvalues. So, you do not really need to have this kind of symmetric equation, but whatever equation you start from, ultimately you will end up with a pair of complex conjugate eigenvalues that look like this. Then we will go ahead. So, you have obtained this. Obviously, there are two eigenvalues, sigma plus j omega and sigma minus j omega. And as we have said, the sigma plus j omega also contain the information sigma and omega. Sigma minus j omega also contain the same information sigma and omega. So, we will not consider them separately, we will start with only one sigma plus j omega say. So, consider the eigenvalue sigma plus j omega. Okay. What will be the corresponding eigenvector? The eigenvector will be obtained from the equation A. Oh, sorry, sigma plus j omega. Sorry, it will be sigma plus j omega. It will be A minus lambda I times x is equal to 0. That will be the eigenvector equation. So, write down the eigenvector equation for this particular eigenvalue, where lambda is sigma plus j omega. Do that. Your A was this. So, I will write them separately, sigma minus omega, omega sigma A minus lambda I would be okay, I will write it separately, sigma plus j omega times 1 0 0 1. Fine. This is the A minus lambda I. So, this will be equal to, do that once, do the algebra once. Okay, sigma minus sigma, it will be 1. So, it will be minus j omega here, here it is minus omega, here it is omega, and here it is minus j omega. Okay, so, that is A minus lambda I. Fine. So, now the eigenvector equation would be then A minus lambda I is j omega minus omega omega minus j omega times x essentially. So, it will be say V 1 and V 2, the two components is equal to 0. Fine. 0 means of course 0 vector. Fine. Now, notice this will give minus j omega V 1 minus omega V 2 omega V 1 minus j omega V 2 is equal to 0 0. Fine. What does this equation say? This minus this equal to 0. Take 1 to this side, you get V 1 is equal to what times V 2? J times V 2. Okay. So, that is the eigen direction. That is why it is a complex eigen direction. V 1 is equal to J times V 2. but that is the eigen direction. You need to choose a vector. As I said, it will not be a unique vector, you have to choose one point and then on that basis the other will be given. Say V 2 is equal to 1, and that gives V 1 equal to j. So, the V 1 V 2 eigenvector will be is j and 1. Happy? That is how you obtain the eigenvector. So, we have obtained one eigenvector which is this, and therefore, the solution corresponding solution will be x of t will be e to the power the eigenvalue sigma plus j omega t times the eigenvector which is j and 1. Right, that will be definitely be a solution, because this is the eigenvalue and this is the eigenvector. Now, break it up. You have e to the power sigma t times e to the power j omega t times j and 1. Now, e to the power j omega t, you know Euler equation? Yes, Euler equation is e to the power j say x is equal to, yes, cos x plus j sin x. So, we will substitute it here. By the way, do you know how to obtain it? How Euler proved it? Yes, yes. You have to expand it. Just expand this one. So, e to the power j x when expanded will give 0 to infinity j x to the power n divided by n factorial, right, which is if you write it in expanded way 1 plus j x minus x square by n factorial minus j x cube by 3 factorial plus x 4 by 4 factorial and so on and so forth, plus j x 5 by 5 factorial, fine. Then club them together, club some of them together. So, we will first put together 1 this the even terms, 1 minus x square by n factorial, sorry 2 factorial plus x 4 by 4 factorial and so on and so forth, we will put in one bracket, plus we will take the j out, this the common factor is j. So, you have here x minus this x cube by 3 factorial plus x 5 by 5 factorial and so on and so forth. This term is and this term is So, this is equal to cos x plus j sin x. It is a remarkable result, all the time used in engineering, and when Euler proved it, nobody knew that it will ever have any application in engineering. Okay, so, where were we? We were here, we will simply substitute it here, it will be e to the power sigma t times cos it will be cos j omega t, cos, oh yeah t minus j.
So, shouldn't we write this expression means we use the other eigenvalue and find the.
Yes, you can do that. I showed that you can always do that, no problem. There are 2 eigenvalues, you can write the equation with 2 eigenvalues, but there are actually 2 approaches. That approach uses both the eigenvalues, but actually 2 eigenvalues do not contain independent information. That is why we chose to have use one eigenvalue, and I show that it is possible to extract two independent solutions out of that only, because there is a real part, there is imaginary part. Real part and the imaginary part independently contain information, that is the point. So, you have plus j sin omega t, and it is j 1 plus, sorry. Fine. So, our job is now to separate out the real part and the imaginary part, which will proceed. E to the power sigma t. Now, we will multiply this. What we have? J cos omega t minus sin omega t, and here it is cos omega t plus j sin omega t. Okay. Now, can you see it? Yes. Now, this is equal to e to the power sigma t remains, and then we will first write the real part, which is minus sin omega t, and here cos omega t plus j cos omega t sin omega t. Fine. So, we have separated out the two parts. Now, you see there are two components of it, one is this, the other is e to the power sigma t times this. So, it is actually p plus j q, and then the argument was that I gave in the last class was that this p and q must both be solutions, because this is nothing but a linear combination of the two components. Multiplying by j is also a linear combination, therefore, these two must independently be solutions and these two are all real. So, this must be a solution and that must be a solution. So, we have then the two solutions as one solution is sigma e to the power sigma t times minus sin omega t cos omega t, that is one solution. The other solution is e to the power sigma t cos omega t sin omega t. Good. If these two are solutions, then the final solution, the general solution x t will be C 1 this plus C 2 that, e to the power sigma t minus sin omega t cos omega t plus C 2 e to the power sigma t cos omega t sin omega t. Okay. So, that is the solution. What does it mean? It means that the individual solution x t, can you write down? This is having two components, x t is C 1, it is minus C 1 e to the power sigma t sin omega t plus C 2 e to the power sigma t cos omega t, and this is C 1 e to the power sigma t cos omega t plus C 2 e to the power sigma t sin omega t. Fine. We have got the solutions. Happy? I am not happy yet. Why? Because I am never happy with solutions of differential equation till I have got back this by differentiating that, right. So, if you differentiate this, you should get back the original equation, just check that. I always do at the exams. Okay. whenever I have a solution of differential equations, ultimately I will have to differentiate it and get back the original equation. If it is true, I am fine. So, differentiate this and check if you get the original equation, which is, where did I keep it? Here. I should get back this. Check that once. This would be anyway, you can do that. I shouldn't bother about this trivial thing, but you should always check, convince yourself, and then only go ahead. Got it? So, if you differentiate these two, you should get back these equations. Have all of you done, or trusting me? Don't trust me. Important thing is that you should not trust the teacher. You should always do it yourself. Happy? You are not doing it. You have done it? Okay. Fine. So, we have the solution as this. Now, what does the solution look like really? Wait. In order to see it, we will do a bit of algebra with this. Is it visible? Yes. So, say we start with this equation y t is this, then y t will be written as this is equal to C 1 plus C 2. So, if I multiply and divide by C 1 square plus C 2 square, then e to the power sigma t will remain, e to the power sigma t is common. Then what you have is C 1 by root over C 1 square plus C 2 square cos omega t plus C 2 by root over C 1 square plus C 2 square sin omega t. Fully feasible? Fine. Now, if I define these things in a suitable way, how will you define? Because I want to extract the phase information from it. So, if I say what?
Take sin omega t plus alpha, where alpha is tan inverse C1.
Yes, that will come. Yes. So, it will be y t is equal to, it will come to be this term will remain. So, it is some magnitude a. So, we will write a is equal to root over C 1 square plus C 2 square a e to the power sigma t, then it will be cos omega t sin cos. Okay, we'll write it like that. So, it will be sin theta cos omega t plus cos theta sin omega t. You can write it like that, which means this is equal to a e to the power sigma t sin omega t plus theta. So, in obtaining this, what have we assumed? A is this, and we have assumed sin theta is equal to C 1 by root over C 1 square plus C 2 square, cos theta is equal to C 2 by root over C 1 square plus C 2 square. So, that this plus this square plus this square is equal to 1, sin square theta plus cos square theta is equal to 1. Then the theta is if we assume this, then it is this. Now, what this is easier to see, easier to visualize than this. Why? Because this tells us that it has a magnitude A, it has a sinusoidal component which has a phase theta, and the phase theta is related to whatever the excitation was there, and then you have this term which is either exponentially decaying or exponentially increasing depending on the value of the sigma. So, if you have y t is equal to a sigma e to the power sigma t sin omega t plus theta, then what will be the behavior be like? By the way, what is x t in that case? What will x t be? X t was, we started with this, do the same manipulation and check what is x t then. Do exactly the same manipulation, cos, yes. So, it is a e to the power sigma t cos omega t plus, fine. So, let us see how does this look like as a function of time. This component is a sinusoid, this component is exponential decay. So, what will be this whole component? It is a damped sinusoid. So, when your t is 0, this term is 1 and this term is 0, therefore, it is sin theta, a sin theta. So, that is where it start. It will start at a value something like a sin theta. Theta gives the phase, right? And then after that, what will happen? After that, this will define some kind of a envelope like this, and your sinusoid will be this is y t, this is t. All right. X t will be a similar thing, but 90 degree out of phase, because one is cos, another is sin. Well, yes. If sigma, he is asking, this will happen only if sigma is negative. What if sigma is positive? Good question. In that case, it will be exponentially increasing envelope, and you will have right for sigma positive t and y. Understood? And the x will also have the same property only thing is that x and y will be out of phase, that is all. Are you convinced? So, that is the result when you have complex conjugate eigenvalues. Now, there will be one case where the eigenvalues are purely imaginary. Let us understand that case first. So, the complex conjugate eigenvalues with purely imaginary special case which means in the lambda is equal to sigma plus j omega, this term is 0, fine. Then your solution originally was x t is equal to this, sigma is 0, therefore, these terms will vanish. What remains will be, I just copy it from there, minus C 1 sin omega t plus C 2 cos omega t, and y t is equal to C 1 cos omega t plus C 2 sin omega t. Okay. What is this? What kind of response is this? Pure sinusoid. So, this behavior will be a pure sinusoidal behavior. But now, let us go a little ahead. What will this behavior be in the state space where you are drawing x versus y? In order to visualize, you just imagine yes, how do you prove it? Yes. So, this actually x square plus y square is equal to 1, this is that. Yeah, that is right. So, ultimately that yields a circular equation, which means the behavior will be like a circle. Now, where do you get this C 1 and C 2 from? From the initial condition. So, depending on the initial condition, it will be a different circle, like this maybe, or like this maybe. Fine. So, if the eigenvalues are purely imaginary, you have circular equation, circular solution. But this circular solution is really what should I say? It is topological circle. It means that if x and y are in the same scale, then only you get circles, and x could be the derivative of y, or y could be the derivative of x. Therefore, there is no meaning to the term that they are really the same scale. So, in general there would be ellipses. In general there will be ellipses. That is why I said they are same topologically circle, because you can stretch and squeeze in order to make them circles. So, in your mind you should carry the idea that they are really circles, but with the pointer that here is x and here is y. One fellow can be the angle of a pendulum, and the other fellow can be the rate of change of the angle. How do you express them in the same scale? Normally you would not be able to. In that case you will get ellipses, that is all. But I mean, when you go back with the concept, go back with the concept of the circle, because of this. Okay. And that is why this specific equilibrium point is called a center. Earlier, when we were considering the real eigenvalue, we said it is a node or it is a saddle. That means the equilibrium point is called a node if the eigenvalues are real and both negative or both positive. It is called a saddle if one is negative, other is positive, but real. But if you have a purely imaginary eigenvalues, then this is called a center, with very obvious reasons. By the way, in which direction will it rotate? Clockwise or counterclockwise? That depends on the wait, there is an easy way of checking it. Suppose you have got this as a solution, right? Suppose you take any point along the x axis. You have got the original equation as, where is the original equation? Here. This is the original equations. Take say this point where y is 0 and x is there. Y is 0 means this term vanishes. So, x dot is something dependent on the value of x. X dot is something. So, x is changing, x dot is there. Y dot is where this is 0 is omega times x, which is positive. Positive means y dot is positive, means a vector like this. Okay. So, that immediately tells that it rotates actually counterclockwise. Or in other words, if this omega is negative term, then it rotates ulta, opposite direction, clockwise. So, we have understood that it will be, if the omega is positive, it will be omega is positive, then it will have vectors like this. So, it will be like this. So, if you start an initial condition here, it will go around it and come back here. If you start an initial condition here, it will go around it and come back here. How about the time? How long does it take for it to come back here, and how long does it take for it to come back here? What does it depend on? Omega. And since for both the C1 and C2 does not depend on omega, it depends on the initial condition, and therefore, in all these the period of revolution should be the same, omega. Frequency should be the same. Clear? So, wherever you may start, it will see the same period of revolution, same frequency. Does it follow from logic? Because your equations ultimately what you have got are these. Where is it? Here are these. That is why the frequency term actually appears here, and if you get an initial condition, say if I say you start from 1 1, you can easily obtain. If I start from say 2 2, you can easily obtain, and you will find that there. So, in those solutions C1 and C2 are independent of omega, and so you have the same frequency for all this. That is one important conclusion. The third important conclusion is that here what does this term do? This term is the exponentially increasing or decaying term. Now, if you have this, so far we were considering purely imaginary eigenvalues, but now if I consider complex conjugate eigenvalues with this, then how will the behavior in the state space change? Notice that we are actually drawing the vector field around the equilibrium point, which in this case is the center. Now, if you have sigma plus j omega plus minus j omega, then the behavior will be dependent on the sigma, say it is a negative value, then it is this, yes, it will spiral towards the center. It will actually go like this. When this is negative, and when this is positive, it will spiral out. Oh, probably it will be counterclockwise direction. So, sigma plus minus j omega is the eigenvalue with this is as positive. Fine, are you through with it? Understood it correct? So, you see we have more or less understood how such what kind of vector fields these complex conjugate eigenvalues give rise to.
The starting point for this spiral would be dependent on the
Initial condition, yes, it will be dependent on the initial condition. See, what we are trying to do is that we are trying to take a snapshot at the region in the neighborhood of the equilibrium point, and we have understood that the region in the neighborhood of the equilibrium point, its vector field will be dependent on the eigenvalues, and so for different possible types of eigenvalues we are trying to obtain the character of the vector field. Let us just do one problem. You know, Galileo made a very important observation. He was sitting in a church and he found a big something hanging from the top that is swinging, oscillating like a pendulum, and he used his own heartbeat to make the measurement and said that it has the same period of oscillation. Independent of the initial condition. So, can you prove it now by deriving the equation for the pendulum? On the basis of this you should be able to. Let us do this. Since you have done the Lagrangian method quite some time back and may have forgotten, that is why let us go back to the Lagrangian method and do it. So, you have a simple pendulum, the one the Galileo saw. It has a angle theta, L, mass m, that is what he saw. Okay. So, in this case your velocity of this one will be L theta dot, right, and therefore, the kinetic energy will be half m L theta dot square. The potential energy will be from this point, how much has it gone up? So, it is minus m g L cos theta. Okay. So, this value. Then your friction term will be half r L theta dot square, where r is the air friction. There will be friction due to air, r is the air friction. So, that is a Rayleigh term. Your Lagrangian will then be T minus V half m L square theta dot square plus m g L cos theta. Since we were not considering the theta as the variable, our variable was position coordinate was q, which is in this case theta, and the momentum coordinate was p, which is the derivative of the Lagrangian with respect to theta dot. So, what was p? Yeah, m L square q dot, m L square q dot. We need to obtain two differential equations. So, that is why I am writing as p and q. So, you have these two. So, this gives immediately q dot is equal to p by m L square, which is a differential equation. So, this is one differential equation. The other differential equation P dot is equal to, how do you obtain P dot? From the Lagrangian equation. Remember, from the Lagrangian equation. So, the first term in the Lagrangian equation yields P dot, and the other two terms are derivative of the Lagrangian with respect to theta, or in this case q, and the derivative of the Rayleigh with respect to theta dot. Just do that. This term will have a negative sign. So, minus m g l, it will be sine, I am replacing theta by q. So, sine q, that gives the first one. Second one will be, it will be plus, no, minus r l theta, not I am not in theta, I am in q dot. Fine. Huh? L square. Yeah, you are right. So, that is the equation for P dot. I will substitute it here, q dot, so that the right hand side is completely devoid of dotted terms. So, this gives minus m g l sine q minus L square actually cancels off. So, you have r p by m. So, this is one equation, this is one equation. Now, let us write these two in matrix form. Just write the equations. Have you written down? So, from there you write it in matrix form. Since we will be now trying to obtain the vector field, let us write it as x and y, p and q. So, you have x dot y dot is equal to, the first term is not there. So, it is 0, then 1 by m l square, here it is minus m g l we are writing the Jacobian matrix. Here we have to differentiate it with respect to q. Sin q will become cos q. And here it is minus, okay, x y. So, the original equations were these. Now, we have locally linearized it, and we have written the Jacobian matrix equation like this. So, this is the local linear description of it. Okay. Not only that, what? No. Okay, let me write it once again. Your q dot was p by m l square. Your p dot was minus m g l sin q minus r p by m. Okay. Now, this is a nonlinear equation, I can see that. So, first we will need to obtain the equilibrium point, and then we will need to locally linearize it along the equilibrium point. Okay, where is the equilibrium point? That is obtained if you set the left hand side to 0. Q dot p dot is 0. Q dot is 0 immediately means p is equal to 0, and p dot is 0 immediately implies this p was 0. So, this whole thing should be 0, and you can easily see there are many solutions of it, because sin q being 0 will happen at 0, 180 degree, 360 degree and all that. So, there will be many solutions, many equilibria. We will come to that later, but at least q is 0 is one equilibrium, So, P is equal to 0, Q is equal to 0 is another equilibrium point. Fine. So, the next step is to obtain the Jacobian. The Jacobian matrix is then the derivative of the right hand side, this is f 1 of P and Q, and this is f 2 of P and Q. The first term in the Jacobian would be this as differentiated with respect to Q. So, this term will be 0. Second will be this differentiated with respect to P, this term will be 1 by m L square. This term will be this differentiated with respect to Q. Fine. This whole thing differentiated with respect to Q will be, this term will vanish and this term will be minus m G L cos Q, right. So, minus m G L cos Q, clear, and the last term will be this whole thing differentiated with respect to P, which is wait, I am yet writing only the Jacobian matrix. From here I am obtaining, and then we will say that okay, now that we need to change the coordinates because these are the local coordinates defined in terms of deviation from the equilibrium point, and then we will say x and y. Presently we are writing only the Jacobian matrix. The Jacobian matrix, this is right, and here it will be R by M. Happy? So, that is the Jacobian. Now, the Jacobian has to be evaluated at the equilibrium point. Equilibrium point is P is equal to 0, Q is equal to 0. Here there is nothing like P and Q, but here there is. So, we have to substitute cos 0 here, which is 1, therefore, it becomes mgl. So, at equilibrium point it becomes 0 1 by m L square, here it is minus m G L, it is minus R by m, right. So, that is the Jacobian as evaluated at the equilibrium point, and therefore, when you have evaluated the Jacobian, then you will say that here is the total system, but now we will define a coordinate system that is valid in the immediate neighborhood of the equilibrium point, let that be x and y. So, there the equation would be x dot y dot is equal to this 1 by m L square minus m G L minus R by m x y. Happy? What are the eigenvalues of this? Obtain that. Obtain the eigenvalues of this. Okay, I leave it to you. Since the time is coming to an end, obtain the eigenvalues of this matrix, and then from there, what can be the solution of this set of differential equations starting from any initial condition. And then from there, try to infer if you can deduce Galileo's observations. That I leave for you to be done in the meantime. Okay, fine. We will meet in the next class.